So if you recall where we left off last time, we've been talking about monitor objects. I talked about what a monitor object was as a concept, a little bit as the pattern, talked about a motivating application that was a buggy queue that didn't have synchronization provided properly. And so what I'm going to do today is talk about the synchronization features that are provided by monitor objects. And we'll start by talking about synchronized methods that are used to provide support for mutual exclusion, and then we'll talk next about synchronized statements. As you undoubtedly recall, mutual exclusion is used to protect shared state from corruption that occurs when multiple threads simultaneously access the state concurrently. And the state in this case is typically fields in classes. So if you recall the discussion about the buggy queue, it was lacking synchronization. We'll talk a bit more about that in a second. And the way to fix this problem is to have another approach that synchronizes the methods. And so there's an example called busy synchronized queue that you can download and play with that shows how to use the synchronization features in Java built-in monitor objects. So we have a busy synchronized queue, which is parameterized by a generic element E, and it implements bounded queue. Bounded queue is this interface that defines methods like take and put and pull and offer and so on. Obviously, the interface by itself just gives you the signatures of the methods, does not provide any synchronization. That's up to you when you implement those methods. So the interface just provides you sort of a contract that you have to implement to provide the semantics that are described in the documentation of that interface. The state that we want to protect, the internal state that needs to be protected against race conditions, includes a linked list, which is not synchronized, if you recall, and also a count of the number of elements that are currently in the synchronized queue. The constructor initializes that state by taking the capacity and storing that in the field and initializing a linked list, which is initially going to be empty. Here are the key methods we're going to focus on. There are other ones, but these are the ones we'll look at. Offer, poll, and isEmpty. And these three methods, as we'll see when we look at the implementations, are what actually add things to the list or remove things from the list in a non-blocking manner, and then check to see whether there's anything in the list. And as you can see from the code here that's marked in red, these are so-called synchronized methods, which means that they're going to be protected in a particular way based on the semantics of built-in monitor objects. Yes, Amanda? So the synchronized keyword is simply an indication to the Java compiler that the methods that are marked as synchronized will be properly provided with mutual exclusion support. So what's your question? Oh, it should say methods using a built-in monitor object. Remember, everything in Java that's not a primitive type at this point is a monitor object. So there's no way you cannot have monitor object capabilities at your disposal. As to whether you avail yourselves of those capabilities is another story. And the way you avail yourselves of those capabilities is by marking things with the synchronized keyword, either in the method signature, as we show here, or as we'll show in the next part, by putting a synchronized statement inside the method. So everything in Java is a built-in monitor object, if you so choose to avail yourselves of those capabilities. What a synchronized method means, if you mark a method as being synchronized, it simply means that that method will be serialized with respect to any other synchronized method that's called on that object. So this is really important to remember. Every object is a monitor object. So if you synchronize the methods, that means if other threads call another synchronized method, or that method itself, on the same object from a different thread, those method calls will be synchronized. However, if you have two different objects with synchronized methods, then two different threads calling those objects won't synchronize with respect to each other. It's only if they're called on the same object. That's the key point to remember. If you think back to our discussions about Java reentrant lock that we had a couple weeks ago, same basic idea. You have this way of being able to ensure mutual exclusion by acquiring and releasing the locks, or locking and unlocking the locks, as is the case with a Java reentrant lock. It's just that built-in monitor objects have support in the virtual machine to do this using compiler directives, whereas Java reentrant lock requires you to explicitly make an instance of a reentrant lock and then explicitly lock and unlock that lock. When you use the synchronized keyword in the method declaration, in other words, when it goes here, then that means the entire body of the method will be serialized with respect to other calls on that method on the same object in different threads, just to make it very specific. So all the code you see here in red is going to be serialized. There's only one method at a time on that object that can be accessing the code in a synchronized method, or in synchronized methods. Interestingly enough, and this is subtle, the synchronized keyword is actually not officially considered to be part of a method signature. It's considered an implementation detail. That's a little bit wacky and wonky, and you can read more about that if you take a look at Doug Lee's website to read about this here. This is important because you can, if you inherit these things, you have to think carefully about how they're used. Okay. In particular, synchronized is not inherited when subclasses override the superclass methods. So if you make another class, synchronized queue, which extends busy synchronized queue, these methods will not be synchronized unless the implementation explicitly synchronizes them, which is non-intuitive. You would think that if something was marked as synchronized, it would inherit that property in subclasses, but it does not. So very subtle, easy to forget, easy to get wrong. By the way, I'll make this quick point here. I tend, because of these quirks, I tend not to like to put the synchronized keyword in the method itself, in the method declaration itself. Instead, I like to put it inside the body of the method, and you'll see how that works in a second. So what are the good things about synchronized methods? Why should we consider using them? They're nice because if you make methods synchronized, then you just look at the signature. If you look at the class and you say, oh, it's synchronized, so you kind of know at a glance it's synchronized. That's sort of good, maybe. The syntax is very compact because you just have to put the keyword, and then everything inside the curly braces, the method body, as it were, will automatically be synchronized. So you don't have to do lock and unlock. You don't have to have try finally, all that kind of good stuff. And the other nice thing is that the method is the unit of synchronization. And that's relatively easy to reason about in many ways, because when you're making a method call, you know that if the method's synchronized and everybody else plays by the rules, then that's the only thing that will run in that object when it actually goes ahead and runs. There are some downsides, however. One of the downsides is that using synchronized, using the synchronized keyword, uses the intrinsic lock, which is this, which is the name of the object whose methods are being invoked. So why is that complicated? What's the problem? Well, the problem is that anybody else can also come along and synchronize on that object. This is a little known fact you'll see more of later. If you have any object in Java that's not a built-in type or a primitive type, you can say synchronized on it. And so in that case, you can end up having sort of confusing semantics, and you can reduce the amount of synchronization, and you can have other threads sort of reduce your own synchronization by making there be more contention, which is kind of bizarre, but that's the way it works. The granularity of locking is also fairly coarse-grained. So locking is on a per object, per method basis. And sometimes that's too coarse-grained because it may actually be the case that within the body of the method, there's only actually a small fraction of the method body that actually needs to be synchronized. There may be only one little place where you're actually accessing mutable shared state. But because you put synchronized at the outside, which means the whole method, you have a broader scope of synchronization. Anybody know why having a broader scope of synchronization could be a bad thing? What's the downside with having a broader scope of synchronization? Joe? Right, you're holding a lock when you don't need it, and why is that bad? Exactly. So what happens there is that you're holding things longer than you need to, so it means that you're impeding or reducing the amount of inherent parallelism in the program, such that if you're running on a multi-core system with lots of cores, things are going to take longer to run. Okay, there's various analogies you could imagine that would help to explain that. Okay, that's the end of the first part talking about synchronized methods. Now that we've talked about synchronized methods, the next discussion we'll talk about synchronized statements. And you'll see that once again, it's all about mutual exclusion and being able to protect the shared state against corruption when accessed by multiple threads. So, as we talked about before, synchronized methods have some limitations. One problem is excessive overhead due to coarse-grained serialization. And maybe a better way to put it, instead of excessive overhead, insufficient leverage of concurrency or parallelism. So we do this at the method level. We talked about that. You always synchronize on the implicit lock, this, which could be a source of contention if somebody else decides to also synchronize on your object. And here's an example that illustrates this. This is actually the Java Exchanger class, which is kind of a wacky class that allows you to exchange resources between two threads at a rendezvous point. I'm not going to talk much about what the class does. I'm just going to use it as an explanation of what not to do. So here's a method called createSlot, and we're going to use that as the discussion of the issue at hand. This is a private method, so it's not called directly by an application client, but it would be called internally. So one approach to implement this method is to make synchronized a method declaration marking. So this is the synchronized method as opposed to what we'll talk about next. So what we're going to do here is we're going to grab this lock. When createSlot is called, it's going to make a new slot. It's going to assign a local variable A to something called an arena, which you can see out here is going to have an array of slots up to some capacity. And then if the indexed location in that array, in this thing, is null, in other words, it hasn't been initialized yet, we're going to initialize it with the new slot. So this is what's typically called lazy initialization, or a first time in check. Here's an alternative way to do this. This uses synchronized statements instead of synchronized methods. So you can see here that instead of having the word synchronized here, it's just a regular old method. And instead, we do some work here with the lock not held. And then only for the part of the code where we really need to make sure it's serialized to avoid race conditions, do we grab this intrinsic lock, do the check, do the update. And this code over here is not protected. So this is what we would say is finer grained, right? Because we don't have to lock the whole method. We just lock the part that actually is accessing shared mutable state. So what we're doing here is we're creating some of the code outside the scope of the synchronization region, so the synchronization region is smaller or narrower. And at least in theory, this will make the code run faster, especially on a multi-core machine where lots of things could go in parallel. So a couple other things. So one way to do this would be to use this to synchronize. That would be one way to do it. But there's another way to do it, which is to use the explicit lock here, which is going to be this thing that's the arena. And the nice thing about using an explicit lock here, as opposed to the intrinsic lock, or extrinsic lock versus intrinsic lock, is that this lock is private, this field is private, so we don't have to worry about contention from other threads synchronizing on the exchanger object itself. So we should avoid additional contention overhead. And we'll talk more about that later in the context of something called the specific notification pattern. There's lots more discussion in the Java documentation talking about intrinsic locks and synchronization, how they work, and so on. So you might take a look at that if you need further information about this. So what are the pros of synchronized statements? So one thing that you can do here is you can use these private fields to synchronize, which we did here. And that kind of hides the implementation details so other things can't come along and synchronize on this unless they know our private implementation details. In other words, if their method's already on the class. And another nice thing is that synchronized statements can be found by searching references to a variable via the IDE. So you can actually find these things. They're just not in the signature of the method itself. The downside is that the syntax is more complicated. So you've got extra stuff. You've got this block here, as opposed to just putting synchronized at the method, at the outskirt of the method, in the method declaration up here. So your code is going to be a little bit more cluttered. Now, in practice, that's not a big deal, but it's a con. So let's talk about something else in this context. And this is a fun discussion about really subtle issues in concurrency control. And this is one of my great contributions to the world of computing, something called the double-checked locking pattern. And I wrote a paper, gosh, almost, well, it's over 20 years ago, I guess, at this point, on something called the double-checked locking pattern. And if you go here, you can read about this. And this launched a whole huge amount of discussion, and many papers were written on this to discuss double-checked locking. And it actually ended up changing the way that the Java virtual machine works in order to be able to support this pattern. So let me explain to you sort of what the pattern is, and then we'll talk about the subtleties involved here. So going back to our exchanger example, here we have the create slot method like we did before, same as we had done. And then down here, we have something called do exchange, and that's just another method, and we'll see how this works. So what we're going to do here is we're going to only synchronize the first time in. So it's lazy synchronization only on the first time in order to make sure that initialization is properly protected from race conditions. So here's the basic idea. When do exchange is called, it goes ahead and it reads the arena at the current index, so it finds a slot, and this is the arena. So this will start out with everything assigned to null. So if the slot is null, then we call create slot, and that's where it does the synchronization. So this check here is actually done in such a way that there's no locking at all the first time, or there's no locking at all when we check this. This is not checked with a lock held. And only the first time in will it synchronize. So we're only synchronizing on the first initialization. After that initialization is done, then the next time in, this will no longer be null, so we'll skip the initialization. And that's what's called the double-checked locking pattern, the double-checked locking optimization pattern. And the reason that this thing works is that reads and writes here are atomic. So this check to slot is mercifully atomic. If that was not the case, we couldn't get away with this clever trick. And you can read more about that to learn about reference reads and writes. So this is a reference read and write because it's indexing into an arena. It's ridiculously subtle. It's a memory management semantic issue of Java. And if you really want to know the gory details, read the material at this link. So the bottom line here is a new slot, this thing done here with create slot, is only created if the current slot is null. And we don't check that with a lock held. So we only synchronize during initialization. All right, so that's a little discussion about the double-checked locking optimization pattern and how you can use it to avoid having to lock all the time. This pattern is very commonly used whenever you implement thread-safe singletons, which is actually how I stumbled upon it in the first place. And it's actually quite fascinating to read about the history of all this stuff. And lots of people have it's kind of like go-to, everybody has very strong opinions about it. So the third and final part of this discussion, we'll just kind of dive a little deeper into the issues we ran into before when we were implementing our buggy queue, and we'll show how busy synchronized queue can fix that set of problems with respect to race conditions. Although keep in mind that this is only a partial solution. We will come up with a better solution in the next lesson. So here's the partial solution. By the way, why is this a metaphor for partial solution? Does anybody know what this is? It's the Chief Crazy Horse Monument, which is not too far away from Mount Rushmore. And it's intended ultimately, when it's done, to be Crazy Horse, you can see his head here, on a horse pointing. But it will probably never be finished because it's taken forever to do it. So it's a partial solution. It's not complete. The example here is in the busy synchronized queue class, and it basically has producers and consumers that are generating messages in different threads and then passing them using a busy synchronized queue. And the busy synchronized queue is loosely modeled on the Java array bounded queue. It's going to implement the bounded queue interface, and it's going to be thread safe but a little quirky. So let's talk about how it would actually work. So as we'll see, we're going to have a busy synchronized queue which implements bounded queue, and unlike buggy queue, which also implemented the bounded queue interface, busy synchronized queue will actually have synchronization in it, as the name suggests. Here's the basic diagram that shows what's going on. We create ourselves a kind of a main test program. We have a producer thread and a consumer thread. Producer thread's generating messages using offer, and the consumer thread is consuming those messages using poll. Offer and poll do not block, as you'll find out if you read the documentation. And they're using the busy synchronized queue to do the passing of messages back and forth. This solution is correct. It works, but it's very inefficient due to busy waiting, and we won't fix that until the next lesson. Here's what things look like. Busy synchronized queue implements bounded queue. We kind of talked about that before. The constructor initializes the fields, and then offer and poll are synchronized methods. So the good news here is that only one of these things can ever be active at a given time within the same busy synchronized queue object. And so we don't have to worry about there being race conditions because that code is now protected. We can't go and add something to the list concurrently to removing something from the list. Or if there was another producer thread, we couldn't add two things to the list at the same time. They would be serialized and protected. Now, this implementation works, but it's got a bunch of problems. One of the problems is that for certain kinds of linked list implementations, certain kinds of implementations of concurrent lists, we actually want to decouple putting something in the head of the list, or at the tail of the list, rather. We want to be able to decouple doing something at the tail of the list from doing something at the head of the list. And that's because if we play our cards right and use other mechanisms such as reentrant locks, where you could have multiple of them, you could actually have a cool scenario where adding things at the end and removing stuff from the front actually doesn't contend with each other because you have two separate locks being used. And you would only end up having contention if there was nothing in the queue or if there's one item in the queue. But otherwise, if there's many items in the queue, adding something at the end and removing something at the beginning can run in parallel because each of those locks, each of those operations is protected by separate locks. So this approach will work, but it may have more contention than we really need because it only has a single lock. So that's one of the liabilities. Adding the synchronized keyword has two effects on the code. You can read about that here at this link. One effect is that you can't interleave these calls, right? So offer and poll are atomic with respect to each other and themselves when called by multiple threads. That's one consequence of having a synchronized method. And the second thing, which is more subtle but very important to understand, to have a fully fledged or full-fledged understanding of synchronization, is that these synchronizers have what are called happens before relationships established. And all that really means in the context of Java and its memory model is that if you add something into the list while you have a lock held, then if someone goes to remove something, it will have the thing added to the list before you try to remove it, assuming it runs in that order, of course. And what happens under the hood is that synchronized keywords will automatically flush the processor caches when you're leaving the method. So when the compiler, when the equivalent of close curly brace is encountered at runtime, this of course is all compiled into the bytecode or the ahead of time compiled code. that has the effect of flushing the change to the data structure such that other threads can then see the element that's been added so they can remove it. So it happens before. And that's basically an important dimension of memory visibility, which is none of the other thing that you get with synchronizers. You get race condition elimination, and so you get atomicity, and you also get visibility. So let's evaluate this approach. So as we talked about before, using a synchronized method has some limitations when used by themselves. We'll fix that in a second. The main problem here is that concurrent calls to offer and poll will busy wait. And in fact, if you were to run this program, if you run the test program using the busy synchronized queue, you'll see that it actually takes a fairly large amount of time to run because it's spending its time, one of the threads is spending its time spinning, waiting for something to happen. And so that's what's going to occur here. It's going to spin. When something calls, the main threads that call offer and poll will end up busy waiting if the queue is empty or full. And therefore, we need to come up with some other more effective means of coordinating offer and poll so they don't actually busy wait when there's nothing to do. Busy waiting would occur, of course, if you try to remove something from a queue that's empty, that'll busy wait, or you try to add something to a queue that's full, that'll busy wait by using the synchronized keyword alone. And therefore, the next lesson we'll talk about other coordination mechanisms like wait and notify to solve that. Okay, so that's the end of the discussion about synchronization and synchronized methods / statements in Java.